us now continue the discussion. So, we were looking at the design of a molecular wire where we have the hydrophobic backbone and we also have the hydrophilic ends as well. And in order to explore the property of molecular wires, that is suitable electron conducting pathways. Now, these conducting pathways were actually or these molecular entities were incorporated into for example bilayers, which are very important in biological self assembly processes. We already looked at the fact that ions need to move from intracellular to extracellular and vice versa, and therefore these signaling pathways involve transfer of potentials, transfer of movement of current, and therefore it is important to see whether the communication between these different boxes or regions can be facilitated by systems which can actually provide the necessary conduction pathways for electrons to move from one region to the other. So, in this regard, a very interesting set of experiments were performed. So, to look at the function of electronic conductivity pathway, the function of electron conductivity pathway, transmembrane conductivity experiments were performed. And these were performed in dihexadecyl phosphate, and this is CH3 CH2 15 O E double bond OH. So, we to start with, we have got this okay. Now we can have them here as well. So, this is the so now what has been observed is that when we have this particular bilayers and now we add this particular molecule of wire here, and here we have K3FeCN6, which is an electron acceptor, and here we have got a donor, that is sodium diethionate. So, this is function as a reducing agent and therefore it will get oxidized, and this is the acceptor because it is going to accept the electrons. So, this is the electron acceptor and this is the electron donor. So, it is to be kept in mind now that now we are performing this experiment in the presence of the zwitter ion. Okay. So, if we do not have the zwitter ion, then what will happen is that the positive you have the phosphate here. Okay. So, only if you were to have this particular molecular wire, then there is no enhancement in the electrical conductivity. Okay. Okay, there is no enhancement in electrical conductivity. So, what I mean to say is that if I were to take this particular A only, so if I take A only as the molecular wire, that means I only have the positive ends. We have the we have this bipyridal moiety where we have the methyl groups, then these positive charges will neutralize the negative charges on the phosphate, and therefore there will be no conductivity which will take place. So, the negative charges on the vesicles will neutralize the positive charges on pyridinium, and no conductivity will be observed. However, when we take small amounts of this deuterium B, now when we are taking this deuterium B in the presence of deuterium B, enhancement in the conductivity takes place by 4 to 8 times, and this enhancement in conductivity takes place because now we have got an internal oxidizing agent, and which is going to get reduced, and we have got an external reducing agent. So, this is an external reducing agent which is going to get oxidized. So, this releases the electron is picked up by this molecular wire, it is transferred, this is the conducting pathway, and then it reaches the acceptor end which is the internal oxidizing agent, and eventually tends to get reduced. So, the electron acceptor property functions here, and therefore, this is the facile conducting pathway, and therefore, in this way the electrons are able to move from the extracellular to the intracellular, or there is a current flow from the intracellular to the extracellular chamber. So, these facile conducting pathways takes place, and therefore, this particular B deuterium functions as an electron conductor, or it functions as a molecular wire. So, this is one very important application of this particular system which actually contains alpha B extensive alternate single and double bonds, which are called the carovilogens. So, these carovilogens which function as a molecular wire having the deuterionic behavior is able to do this conducting process very facile way. Keeping in mind this application, the next thing was that if you have got a molecular wire, we would also like to protect the molecular wire using some particular insulation, which is referred to as a molecular cable. So, a molecular cable was also designed. A molecular cable has also been designed, which can actually insulate the molecular wire. Let us look at one particular example of this. So, now you can see a pretty long structure, and effectively tells you that we have got these molecular cables, and it is a three-stranded molecular cable, and this was again designed by Jean-Marie Lai, and this is to actually contain the carovilogens. So, you have got this carovilogens, this molecular wire here. So, this molecular wire which is present inside can be insulated using this 3 standard molecular cable, because the carovilogens are delicate. As you know, the molecular wire are the delicate entities, and therefore, you can actually cover them with these molecular cables so that they stay protected. So, we see we can actually design molecules, very complex molecules, to function as molecular wires as well as molecular cables. The next application is we can look at is molecular switch, a molecular switch process. So, let us take this particular example where this particular system functions as a molecular switch. This system is a very popular system. It has been studied and investigated in detail. This is a methyl and this is a methyl. So, this is the open state of the system, and this is in equilibrium with the closed state. This is the methyl. R2, and this is the closed state. So, now in the closed state you can see that we have this rearrangement of the electron density, and this gives rise to the closed state. Now, the open this cyclic the closed state is obtained when you irradiate with 365 nanometer light, which is the UV light, and when you irradiate it with 600 nanometer or greater, that is the visible light, it gives rise to the open state. And we can have two different case studies. For example, case 1 where R1 is equal to R2 is equal to this N plus. We can write it here as well, and we can also have R1 is equal to and R2 is equal to so this behaves as a donor and this behaves as an acceptor when you have R1 is equal to this particular moiety, which is the donor, and this is the acceptor. So, there are some very interesting properties of this molecular switches, and so you are able to access first of all the two stable states as a function of wavelength. So, the switching and this switching on and off process is completely reversible depending upon the wavelength of light you use. If you use UV light, it will go to the closed state. If you shine visible light, it will come back to the open state. And the electronic properties of the two states are also very different. For example, you can see here that the closed state contains a fully conjugated bridge. So, you see the alternative double single, this kind of a conjugation pathway is there. This is the nice conjugation pathway which is there in the closed state, a fully conjugated system, and therefore, this allows for effective electronic communication, say from R1 to R2. So, say if R1 is a donor group and R2 is an acceptor group, the donor group is able to push electron density and the acceptor group is able to accept the electron density via this conjugation pathway, and that makes this closed state a very interesting situation where electronic communication can take place between the donor and the acceptor groups. And also when R1 and R2 are same, for example, here both of them are positively charged, this conjugation pathway effectively insulates the two positively charged species as well, that is they stay away from each other in the case of case 1 where both are positively charged. And this is a very interesting case of molecular switch. And what happens is that this electronic communication essentially between the donor and the acceptor is what constitutes a push pull system. And this push pull system is very important because these kind of molecules exhibit NLO properties, which is called the non-linear optical response, and this essentially is characterized to start with a large magnitude of the hyperpolarizability of the system of interest, a large magnitude of the hyperpolarizability of the system of interest. And this actually happens in the case of the molecular switch in the closed state, that there is very facile electronic communication, there is extensive polarization and from one end to the other, because there is the donor part and the acceptor part, and therefore this creates a ground state charge separation between the donor and the acceptor moiety. So in the ground state you now have got a high magnitude of the dipole moment, and therefore this molecule which has got a high magnitude of the dipole moment can now interact with the external electric fields, and this external electric field can now polarize the electron density in the molecule. In addition to it polarizing it in a linear fashion, non-linear responses are also present, and this has to be incorporated into the overall polarization of the sample, and out of which the non-linear response becomes important, and that is reflected in the large magnitude of the hyperpolarizability coefficient, which can actually be computed for a system of interest as well. So now what is to start with a NLO response? Let us look at the basic principle of a NLO material. The NLO response is also referred to as second harmonic generation, and effectively this phenomena causes the doubling of the frequency of the incident light. So if you shine light of a frequency nu, what comes out is the frequency 2 nu. For example, these NLO experiments are actually done on powdered samples. On powdered samples using the Coutts-Perry technique, where you actually take a capillary, a glass capillary, fill it with powdered sample. The sample can be organic, inorganic material, and you shine light of 1064 nanometer, and what comes out is the green light of 532 nanometer, indicating second harmonic generation which is present in the material of interest. And so what we can now see that when you actually shine a light of a particular frequency omega, the extent of polarization in the molecule mu, which is a function of the frequency, is actually has got a linear component, but it also has got a non-linear component as well. And so to start with, the linear component is alpha ij omega, but now when you subject it to very intense fields, when you subject it to very intense fields, on being subjected to very intense fields, for example lasers, then the extent of polarization which is induced in the sample is the extent of polarization is nonlinear. Okay, and this is because that the overall polarization is asymmetrical in nature, and because it is asymmetrical in nature, therefore it now contains, in addition to the linear polarization, it also contains the nonlinear terms, such that we can now refer to the dipole moment mu is equal to the ground state dipole moment plus alpha ij e plus beta ij k plus gamma term comes in, and these are the nonlinear terms. This is the linear response. And beta and gamma are referred to the first and second order hyperpolarizability. So these are the first and the second order hyperpolarizability terms, and so this beta term is actually the second harmonic generation term or the NLO response. And in order to get a nonlinear optical response, what is also relevant in the solid is that the arrangement must be non-centrosymmetric. If the arrangement of the molecules is such that there is center of inversion in the crystal, then the overall polarization is equal to 0, and therefore there will not be any such SHG response. Now going back to the previous term here, you can see that we can write now E is equal to E0 cos omega t. So that will make it mu 0 plus alpha ij, and the electric field E is equal to E0 cos omega t plus half beta ij k E0 square cos square omega t plus 1 by 6 gamma E0 cube cos cube omega t. And now we know that cos square omega t is equal to half plus half cos 2 omega t. So therefore we now see that the electromagnetic radiation contains a component which is oscillating at 2 omega or twice the frequency. So this oscillating frequency is twice the magnitude or double the magnitude of that of the incident frequency, and therefore you will see now that if the frequency is double, this leads to lambda being half the initial value. So that is what happens is that when you have 1064 nanometer, what comes out is now 532 nanometer green light. So the wavelength is half, the frequency is double, and that is the origin of the SHG response. And so what is also very important is that the design of NLO materials. So if you are going to have materials which do not have high magnitude of the hyperpolarizability coefficient, that is beta, then they are not going to function as efficient NLO materials. Number 1. Number 2, we also need to arrange the molecules in a non-centrosymmetric fashion. So the design of an NLO material is that number 1, large polarization, and number 2 is the non-centrosymmetric arrangement. Non-centrosymmetric arrangement. So if you are able to have these two conditions satisfied, then we can elicit a very efficient response for a material to exhibit NLO activity. And there are different ways in which this NLO response has been achieved, and people have tried to design systems which exhibit marked polarization. So if you want to see marked NLO effects, then the design of the system has to be such that overall, that when you excite the molecule, there is a large charge separation created, there is sufficient amount of polarization in the material, and so we need to have large changes in mu and small energy gap between the ground and excited state. So in this regard, people have designed different kind of systems which we call as push-pull systems. The molecular switch was one such example, but we can take more examples. For example, we can have a donor system, and we can have a communication with an acceptor system. For example, we can take this is one system, and now we can increase the conjugation. A, or we can have so this can push electron density, this is the donor and this is the acceptor, and we can increase the conjugation here as well. And A can be of different types. It can be an electron withdrawing group like an aldehyde. It can be a cyano. It can be a protonated pyridine, or it can be strongly electron withdrawing cyano or a nitro group. So these can be my acceptor moieties, and these are my donor functionalities which you see here. These function as efficient push-pull systems, and to start with, the molecule is expected to have a high polarizability. But now if this molecule which has got a high polarizability arranges in the solid state in a way that the dipoles they align in a non-centrosymmetric way, or they orient in a parallel fashion, then this will give a large bulk polarization, a large bulk dipole moment. But if they arrange in a centrosymmetric way, then the dipole moment will simply be equal to 0, and the overall bulk polarization will be equal to P will be equal to 0. So in a crystal, if you have the opposite arrangement of these dipoles, then you will not be able to get any overall SHG activity. Although at the molecular level you might have designed very efficient push-pull systems, but the arrangement simply makes it centrosymmetric, and therefore you are not able to elicit a good SHG response. So, you can have a molecule which can have, for example, polymorphs, where one polymorph can have a non-centrosymmetric arrangement and the other polymorph can have a centrosymmetric arrangement, and one is SHG active, another is SHG inactive, and that is what makes design of SHG materials extremely challenging and interesting, because it is not in solution, but it is in the solid state that we are trying to look for the SHG property as well. And the idea is always to be able to align the dipoles in a non-centrosymmetric manner, so that you can extract or utilize the hyperpolarizability contained in the molecule of interest. So, with this we come to the close of the discussion of SHG materials. In the remaining lectures we will look at some other aspects of supramolecular chemistry as well. Thank you.